let's say that you have to travel to many cities, okay, one after the other, but you can choose the order, and you want to make your trip the quickest and the cheapest. Okay, so how should I fly from one city to another so that it will take the least amount of time and the flight ticket will be the cheaper? If you have 10 cities, a normal computer today, a powerful computer will take about, I don't know, 20, 30 seconds to solve the problem. If you have 15 or 20 cities, it will take about 10,000 hours. And if you have 35 cities, it will take the age of the universe. So it's an unsolvable problem. Quantum computers are not machines that work faster. They're not faster than normal computers. A machine that look at a problem in a totally different way. Instead of looking in a serial way to the problem, trying one trajectory and then another trajectory and then a third trajectories of all these flights and try to find, and if you go all the trajectories before you find the best one, right? Until you really get to the end. The quantum computers can look at the whole problem in one single step, basically.
A computer is made of bits, right? And each bit is like a light bulb, and it can be either off or on. This is a bit. And in a classical computer, in a computer like the one we all have on our desks, in a classical computer we have many bits, a huge number of bits. Each one of them at any given minute, at any given time, is either connected or disconnected, 0 or 1. In a quantum computer, each bit will be at the same time 0 and 1, or at the same time connected and disconnected. So you'll have a computer that is at the same time in a huge number of states, all moving together to compute the question, to solve the question that you gave the computer. But the condition is that you will not leave while you go here or here. You will not leave neither here nor here any sign, any recording that gives away the fact that you were here.
So this entire room is actually one transistor. So we take a one photonic qubit into one atom and swap their information, but you see that miniaturization is not the strong side at the moment, because this one room is one gate, whereas in a smartphone you have 10 to the 9, you have billion gates like this. It's very hard to build a machine with thousands of millions of qubits in one place, because you have to really control all of them, make sure they're at the right state, and that's becoming more and more complex as you have more and more qubits on one chip. So eventually, and most probably, every quantum computer will have to use smaller modules, which are more manageable, like, 100 qubits, 1,000 qubits, but not more. And they communicate between them somehow, and that somehow is almost definitely going to be light. Single particles of light, more specifically, which are called photons. And this, in fact, is what my lab focuses on. Taking a qubit, information which is not only 0 or 1, but can be 0 and 1 at the same time, and taking it from a qubit, in our case is an atom, transferring it to a single photon, a single particle of light, going through an optical fiber, and then mapping to another atom. So it's like a read and write. We're very proud of this experiment, but it works for only a few millionths of a second every second. I don't need to build a universal quantum computer. Universal meaning that it solves everything. Any example I give it. I want to solve specific problems. For example, how a molecule behaves, or how some glass would break. Some physical system, and it's very hard to simulate it on a regular computer.
Where would that be very, very important? It could make a huge impact. For example, drug design. Think about how you design a drug. You have many atoms, molecules, that you need to place at the right position so that it can fit, let's say, into a protein or something like this. You know what? That problem of creating a molecule that would fit the right protein is the same problem as you traveling to 30 different cities and finding the best way to go. It's the same problem. But there's no 30 atoms, there are lots of atoms. So it's an unsolvable problem using a computer. If we have a quantum computer, we can design drugs in a computer in a way that it's impossible to do today.
When you send your debit card or Visa information over the internet, it's being encrypted somehow, and the key for this encryption is distributed between the parties, the bank and you, and a quantum computer could potentially break that code.
We'll reach this point. It will be misused one way or another. Okay? And the question is how we control this. We can do that, I would say, there are two different ways. One is regulations, and we need regulations. And the other one is, of course, education. Education is way more powerful, okay? But we need to invest in it a lot, and we don't do that.
Could quantum computing some way destroy free will?
Think about two people having a car accident in the street. But if one of them would have brushed his teeth just for 2 more seconds, then he would not cross the road at the same time. And so I have doubts that we can get over the free will, because I have doubt that we can measure and know what are the small details that they're making our life changing so much. Small things we do at a certain moment can have huge impact a day, 10 years, or 50 years later.
Quantum computing is real. It's available today. Both IBM, D-Wave, Rigetti, Intel, Google, all have and are using quantum computers of some kind of design and some level of maturity.
Come il quantum computing cambierà radicalmente le nostre vite?
That it reduces the amount of electrical power needed for computing. So we can solve the same problem either classically or quantumly, but the quantum computer is going to take a lot less electrical power. But in a classical computer, you have to understand the system entirely before you can write a program that simulates it and then allows you to study its behavior. In quantum computing, you don't have to understand the whole thing first, like you do in classical. And so therefore, you can use it as an aid to discovery and creation and invention. And that's going to be the main thing that quantum computing does in the future, I think.
We don't need to guess the future. We just need to invent it.